Assalamu alaikum. So in the previous lecture we were discussing about a little bit about auto transformer. So we come across uh, the different types of the auto transformers, whose core sometimes was made of a rectangular type and sometimes it was made of circular type. Usually uh, we can make an auto transform from a two-winding transform by simply having connecting this winding to this, or we can make a connection between D and C and take the output from, let us say, from this C and this B. You can see from here we're taking this winding to this and then connecting this D and C, taking the output connection from C and B and giving the input between A and B. The resulting transform, which is known as auto transform, will be like this. So this is how sometimes you can make an auto transform from a two-winding transformer. So two-winding transformer is a transformer which has the two separate windings or separate limbs which are electrically isolated by some magnetic material, and they are coupled through this magnetic flux here. They are connected directly electrically. There is a direct connection between A and C, and there is magnetic coupling as well. Let us first discuss about the working of an auto transformer. So when AC voltage V1 is applied to the winding AB, AC voltage is applied to the winding AB, that is here and here, an exciting current starts flowing through the full winding AB. Exciting current will flow through this winding. If the internal impedance drop is neglected, then the voltage per turn in the winding AB is V1 by N1. That means the voltage over total voltage divided by total turns will be equal to V1 by N1. So voltage per turn will be given by this. And therefore the voltage across BC, it has a number of turns N2, voltage at this will be equal to N2 multiplied by the number of voltage per turn, that is equal to V1 by N1. So it will be equal to V1 by N1 into N2. When the switch S is closed, a current I2 starts flowing through the load and the current I1 is drawn from the source. Definitely that has to balance the MMF. We will come to that as well. So input power will be equal to output power when we neglect the losses. So V1 I1 cos of phi1 will be equal to V2 I2 cos of phi2. If the internal leakage impedance drops and the losses are neglected, then phi1 cos of phi1 will be equal to cos of phi2. We can say that this is then we can say this is an ideal transformer. Then V1 I1 will be equal to V2 I2, or V2 by I1 will be equal to I1 by I2, which is equal to N2 by I1, which is equal to K. So from here on we will be using this K as the voltage transformer ratio from output by input, where we are assuming output to be less voltage as compared to input. So K will be taken as less than unity. The expression is identical to a two-winding transformer. Let at any instant the exciting current flows from A to B, and it establishes the working MMF directly vertically upwards. Definitely when the current is like this, we can see the flux will be upwards, and it may be downward depending on the winding sense. Let us say winding sense is such that so that the working flux is showing an upward direction. When the switch S is closed, the current in the winding BC will also start flowing from B to C, because the current direction here will be like this. I2 will start from flowing B to C. In order to create the MMF opposing the exciting or the working MMF as per the Lenz's law, definitely if the current flowing in this winding is like this and the working flux is upward, so by Lenz's law the opposition will be in such a way so that the flux will be downward. Just to create the flux downward, I2 has to be upwards in that case. Since the working MMF in a transformer remains constant at its no load value, the primary must draw the additional current I1 from the source in order to neutralize the effect of current, that is IBC. So since the flux will now reduce due to this current flowing in the secondary, but the flux in this winding should remain constant because we are supplying the transformer with constant voltage and frequency. So to balance that, it will draw more current from the primary so that the net flux in this remain constant, because when current is increased, this MMF, that's N1 and I1 will also increase. In the winding AB, I1 flows from A to B, I1 flows from A to B. while the winding BC, I2 flows from B to C, I2 will flow from B to C. Therefore, the current in the winding BC is I1 from C to B, I1 will be from C to B, and I2 will be from B to C, I2 will be from B to C. Here, the current I2 is greater than I1 because it is a step-down transformer, because V2 is less than, and their MFs are opposing each other at every instant. Therefore, IBC, the current in this will be equal to I2 minus I1. So MF of winding A and C, so MMF that's produced by the winding this will be equal to number of turns multiplied by the current flowing through this. The number of turns in the winding AC will be equal to N1 minus N2 multiplied by I1. So it will be equal to I1 N1 minus I1 N2. So since I1 N1 is equal to I2 N2, which we have just seen from this is I1 N1 is equal to I2 N2. So that means I2 N2 minus I1 N2, that taking N2 common, it will be equal to I2 minus I1 into N2, I2 minus I1 into N2. So, but this is the value of the MMF in this winding. You can see the current in this is I2 minus I1, and the number of turns in this case is N2. So this is the MMF of the winding C. Therefore, it is seen that the transformer action takes place between the winding section AC and the winding section BC. There is also a transformer action between this winding and this winding, since we have proved or derived their relation and they come to be same. In other words, the volt ampere across winding AC are transferred by the transformer action to the load connected across BC. This is very important because apart from the conduction, that is the direct connection between this and this, the transformer action also takes place between the winding AC and BC. So power transferred in VA, that is the power transfer inductively from this winding to this winding, that will be VAC into IAC, that is equal to V1 minus V2 into I1. Total power transferred or input power, that is total power which is transferred, which is the inductive power transfer plus conductive transfer power, that will be equal to V1 into I1. So power transferred in VA and input power in VA will be equal to V1 minus V2 into I1. Here it will be divided by V1 I1. So I1 and I1 cancel out, to be equal to 1 minus V2 by V1, so 1 minus K. So power transferred inductively, that is by the transformer action, will be equal to 1 minus K into power input. Out of the input volt ampere V1 I1, only VAC, that is V1 minus V2 into I1, that is this one, is transferred to the output by the transformer action. So this much of the power is transferred by the transformer action, and you will see that this will be same as that was transferred by the two winding transformer if it would have been a two winding transformer. The remaining power in volt ampere required for the output are conducting directly. They are conducted due to this direct connection, electrical connection, to the secondary from the primary due to electrical connection. Now power conducted in VA will be equal to total power minus power transferred. So total power is V1 I1 minus V1 minus V2 into I1, so V2 I1. So power conducted in VA, that is this one, V2 I1, divided by power input in VA, that is K. That means power conducted will be total power multiplied by this K. So power transferred will be 1 minus K into input power. Power conducted will be K times input power. This power transferred is also known as power transfer inductively. So considering the equation, we can calculate this power transferred inductively or power transferred in terms of voltages. So power transferred divided by power input will be 1 minus K. So 1 minus V2 by V1, it's V1 minus V2 divided by V1. So inductively transferred power divided by total power will be high voltage minus low voltage divided by high voltage. You can directly use the voltage relation to calculate its value. Now the saving of copper in an auto transformer. We have actually a lot of saving when we use a two winding transformer as an auto transformer. Volume and hence the weight of copper or aluminum is proportional to the length and the cross section of the conductor, because volume is equal to this length into the area, and hence weight will be equal to this volume into density. Let us say that this density is constant, so this weight will depend upon the length and the cross section area. The length of the conductor is proportional to the number of turns. As the number of turns increases, length will increase automatically, while the cross section is proportional to the current, because we are actually providing the cross section of the conductor as per the current requirement. So we can say the cross section is proportional to the current. Hence, the weight of the copper is proportional to the current and the number of turns, or we can say mm. Now, with reference to the following figure, that is this and this, weight of the copper required in an auto transformer, that is for this case. So WTA is equal to weight of the copper in section A, AC, that is here, and weight of the copper in section BC or CB, that is here. So it will be mmf in this and mmf in this. mmf in this will be equal to I1 into N1 minus N2, that is this. Here mmf will be I2 minus I1 into N2, that is this. So which will be proportional to I1 N1, that's multiplying this, minus I1 N2. That is I1 N2 will be over here minus. This will be equal to I2 N2 will be plus, and I1 N2. I2 N2 will be here, and one term has been added to this. So this is the weight of the copper. In case of auto transformer, it will be I1 N1 plus I2 N2 minus 2 times I1 N2. If an ordinary two-winding transformer is to perform the same duty, then with reference to the following figure shown below, that is for this case, its weight of the copper will be proportional to N1 I1 plus N2 and I2. That's N1 I1 plus N2 I2. Now the ratio of the weight of the copper in an auto transformer to the weight of the copper in an ordinary transformer or two-winding transformer is this. That is I1 N1 plus I2 N2 minus twice I1 N2 divided by I1 N1 plus I2 N. Taking this term separate, as I1 N1 plus I2 N2 divided by I1 N1 plus I2 N2, it will be equal to 1. And this I1 N1 will be equal to this. It will be equal to 1 minus twice I1 N2 divided by twice I1 N1. Let us say it is like this. So this 2 and 2 will cancel out. I1 and I1 will cancel out. It will be N2 by N1. N2 by N1 will be equal to K. So this whole term will be equal to 1 minus K. That means weight of the auto transformer will be 1 minus K times weight of the two-winding transformer. Now what will be the saving of the copper in auto transformer? It will be the, because weight of the two-winding transformer will be more as compared to the weight of the auto transformer. So we'll subtract the weight of the this two-winding transformer minus weight of the auto transformer. So weight of the two-winding transformer minus weight of the auto transformer, weight of this two-winding transformer is WT0 minus 1 minus K WT0, because this is the weight of the auto transformer. So it will be equal to K times WT0. So that means saving will be K times weight of the copper required for the two-winding transformer. So hence the saving of the copper increases as the transformer ratio approaches to unity, or we can say it becomes more effective. The auto transformer becomes more effective as it reaches to the, as a transformer ratio reaches to the unity. Therefore, auto transformers are mostly used for the K nearly equal to unity, or we can say it is usually used in the range of 0.5 to 1.5, 0.5 to 1.5, K is equal to 0.5 to 1.5 range. Now let us discuss about the advantages of auto transformer over the two-winding transformer. The quantity of the conductive material required is less, as we have discussed just now. The quantity of the conductive material required for an auto transformer having the same rating as that of the ordinary two-winding transformer is only 1 minus K times. That is, the quantity of the conductive material required for an auto transformer is equal to 1 minus K times quantity of the conductive material required for an ordinary two-winding transformer. Thus, the cost of the auto transformer is less as compared to the two-winding transformer of the same rating. So its cost will be less, hence we are always using the auto transformer. As you will see that in offices, in you can say domestic applications, in houses, in homes, we are using mostly auto transformers. Quantity of the magnetic material required is less. During the design, the window dimensions are decided from the consideration of the insulation and the conductor material. For the auto transformer, since there is a reduced amount of the conductor material, it means the lower window area is required, and therefore smaller core length is also required. It shows that for the same core area, the window height of the auto transformer core is less. Hence, there is a further saving in the core material. Thus, the auto transformer is more economical than the two-winding transformer when K approaches unity. When K approaches unity. Operating efficiency is higher. Owing to the reduction in the conductor and the core material, the ohmic losses in the core conductor and the core loss are lower. Consequently, the autotransformer has higher efficiency than the two-winding transformer on the same rating. Operate at a better voltage regulation. Again, reduction in the conductor material means lower value of the ohmic resistance, because as the length of the conductor is reduced, the resistance of the conductor will also reduce. A part of the winding becomes common. That means leakage flux or the leakage reactance is less. When leakage flux is reduced, automatically leakage reactance will also be reduced. In other words, the autotransformer has lower value of the leakage impedance, and hence autotransformer has a lower value of the leakage impedance and has a better voltage drop across this leakage impedance that result in the better voltage regulation than the two-winding transformer of the same output. But there is one main drawback of the autotransformers which actually hampers its use in widespread, in every part of the power system. Although autotransformers have less cost, better regulation, and low losses as compared to the ordinary two-winding transformer of the same rating, but still they are not widely used due to one major disadvantage, that the secondary winding is not insulated from the primary. If an autotransformer is used to supply low voltage from a high voltage, so you can see there is not any isolation of the secondary winding from the primary winding, and if by chance we are using this autotransformer to supply a low voltage from a very high voltage, and there is a break in the secondary winding, and if there is a break in the secondary winding, you will see that full primary voltage come across the secondary terminal, which may damage or which will be dangerous to operate in the equipment load. So in that case, it will be very dangerous if the secondary winding gets disconnected by some. Therefore, it is advisable not to use an autotransformer in the high voltage or low voltage system. Their use is only limited to the places where slight variation of output voltage from the input voltage is required. That is why this is one of the one more reason why do we use its variation close to unity, even if that is the case, because for example, if we change this 220 to, let us say, 210, even if in the secondary we have a break, only 220 voltage will appear across the secondary, which is close to the 210, which is designed for this. So in that case, it is used like this. So for very high voltage to low voltage, that means K having very small value, less than 0.5, let us say 0.2, 0.1, it is usually avoided. The other disadvantages are the effective per unit impedance of an autotransformer is smaller compared to the two-winding transformer. The reduced internal impedance results in a large short circuit current or fault current. So since effective impedance is less, if the short circuit occurs at the input terminal, you will see that it results in a large fault current. In an autotransformer, there is a loss of isolation between the input and output because of a direct connection. This is particularly important in three-phase transformers where one may wish to use a different winding and earthing arrangement on each side of the transformer, because this is not the case when we use autotransformer because they are directly linked. But in case of isolation, we may have isolation, we may use different winding for different purposes. Now let us discuss about the simplified equivalent circuit of an autotransformer. Simplified means, already if we use the equivalent circuit, we have to find out its primary impedance, then the parallel branch and the secondary impedance. We can use the equivalent circuit like this, simplified equivalent circuit. We can use the parallel branch at the input side, and we can club the this resistance and the reactance on the secondary side, or we can say on the right side of the parallel branch, or parallel magnetizing branch. So that's why we have here used the word simplify. Now an autotransformer shown in figure A, that is this one, may be considered as a two-winding transformer with winding of section AC of N1 minus N2 term acting as the primary, and the winding of section BC of N2 term acting as the second. So we can consider this transformer as a two-winding transformer where N1 minus N2 will act as a primary winding, and the current flowing through this winding is I1, and N2 will be having the secondary winding and the current flowing through this I2 minus I1. So In that case, we can consider it to be a this two winding transformer. And by considering it as a two winding transformer, it is then very simple to draw its equivalent circuit. Thus, an autotransformer behaves the two winding transformer. Primary applied voltage across VAC is across AC is VAC, and the primary current is I1. That is what here. The secondary output voltage is V2 and the secondary winding current is I2 minus I1. For a given autotransformer, its equivalent circuit as a two winding transformer is shown in figure B, that is there. Neglecting this exciting current or the parallel branch, the autotransformer can be analyzed as a two winding transformer as shown in figure B. So it becomes very simple in that case. That the primary winding impedance ZAC is equal to R1 plus JX1, that is the leakage reactance and the resistance of the primary winding, N1 minus N2. Secondary winding impedance ZBC, that is over here. It has its internal resistance of R2 and the leakage reactance of X2. Primary current IAC is equal to I1. IAC will be equal to I1. Referring all parameters on the primary side, that is on this side, that means this will be then equal to R equivalent or apparent will be equal to R1 plus R2 dash, where R2 dash will be the resistance of this referred to this side. Then the resistance of this referred to this side will be equal to R2 dash will be equal to R2 into N1 minus N2 divided by N2 whole square divided by this N2 whole square. That is equal to R1 plus R2 into 1 minus K, because when you divide it by N2, here N1 minus N2 divided by N2, it will be equal to 1 minus K divided by K whole square, because we have assumed K to be equal to, what is the value of K? That is V2 by V1, which is equal to N2 by N1. Yes, it is N2 by N1. So it is N2 by N1, 1 minus K. 1 minus K minus 1, it will be equal to 1 minus K divided by K whole square. Similarly, for total X, it will be X1 plus X2 dash, that is X1 plus X2 into N1 minus N2 divided by N2 whole square. It will be like this. So here also, as I have told you, that we have used here the simplified equivalent circuit. We assume the parallel branch exciting current to be neglected or on the input side of the transformer. So the secondary voltage referred to primary side, that is V2 dash at this point, that will be equal to N2 minus N1 minus N2 divided by N2 into V2, that is 1 minus K divided by K into this, and VAC will be equal to V2 dash plus I1 into ZAP. So VAC is equal to V2 plus 1 minus K divided by K plus I1 into R1 plus R2 into 1 minus K divided by K whole square plus J times X1 plus X2 into 1 minus K divided by K into R square. So this is the total equation of the VAC. Now VAC will be equal to, or in general it can be simplified like this, V2 into 1 minus K minus 1 into I1 SC. This is REP, this is JXEP. So from figure A, it reveals that V1 is equal to, now what is the V1 equal to? Let's see from here. V1 is equal to VAC plus this V2. VAC plus V2, VAC is this value and V2 is as it is V2 like this. So when you simplify it, this will be equal to V2 into 1 by K minus V2. This V2 and V2 cancel out. So V1 will be equal to V2 by K plus this I1 into REP plus JXCP. So this is very important equation. So it will be used to find out the voltage regulation or some other parameters of the transformer, autotransformer. Now this is the equivalent circuit, as I have told you. In this case, we have assumed this parallel branch on the input side, and in this case, we have assumed it to be neglected. So REP, this is I1. So this is I0. This is total. Let's say this is total current I1. This is the input current. So I1, this REP is equal to R1 plus R2 dash. That is equal to R1 plus R2 into N1 minus N2 divided by N2 whole square. That is equal to R1 plus R2 into 1 minus K, the K whole square. That will be equal to REP or REP. XCP will be equal to X1 plus X2 dash plus X1. That is equal to X1 plus X2 into N1 minus N2 divided by N2 whole square, plus that is equal to X1 plus X2 into 1 minus K divided by K whole square. So in this way, we will be able to find out the equivalent circuit of an autotransformer. Now let us try to compare the characteristics of autotransformer and the two-winding transformer. An autotransformer can be considered as a two-winding transformer with winding AC as a primary and winding BC as a secondary, as I have told you just now. Ratings and characteristics of the two-winding transformer, autotransformer and the two-winding transformer so obtained differ as discussed below. So we'll discuss them. The first one is the rating. It is seen that the winding AC acts as the primary and the winding BC as the secondary of the two winding transformer. Then considering the input side, kV rating of the auto transformer divided by kV rating of the two winding transformer. So what is the kV rating of the auto transformer? That is primary input voltage V1 multiplied by primary input current I1. That is primary voltage across the AC, primary voltage across the AC multiplied by primary current of the AC, like this. So this will be V1 I1, that is this V1 into I1 auto transformer input VA, and the two winding transformer input VA will be equal to V1 minus V2, that is voltage across AC is V1 minus V2 into I1. So I1 and I1 will cancel out. It will be equal to, when you divide by V1 on numerator as well as on denominator, it will be equal to 1 divided by 1 minus K. So considering the output side, kV rating of the auto transformer, that is equal to V2 into I2, V2 into I2, kV rating of the two winding transformer, that is V2 into I2 minus I1. V2 and V2 will cancel out. When you divide it by I2, it will be equal to 1 divided by 1 minus I1 by I2. It's again equal to 1 divided by 1 minus K. So the kV rating of the auto transformer will be equal to 1 divided by 1 minus K into kV rating of a two winding transformer. It will definitely be more when K is less than 1. Let us say K is equal to 0.9, 1 minus 0.9 will be equal to 0.1, 1 divided by 0.1 will be equal to 10. It will be 10 times the kV rating of the two winding transformer. The second one is the loss. When the two winding transformer is connected as an auto transformer, the current in the different sections and the voltage across them remain unchanged. You can see from here the current. This is the auto transformer current. Here in this section is I1. Here also the current is I1. In this section current is I2 minus I1. Here also the current is same, I2 minus I1. So the current in the different sections remain unchanged. Therefore, the losses when working as an auto transformer are the same. Losses will remain the same as there's a losses in the per unit transformer. Losses, actual value of the losses will remain the same, but per unit losses, however, differ. That is per unit full load losses of an auto transformer divided per unit losses, full load losses of the two winding transformer. That is full load loss divided by kV rating of the auto transformer, kV rating of the, this is full load loss divided by actually kV rating of the two winding transformer. It will come upwards. Then this full load loss the same. It will cancel out. It will be again the same thing. That is kV rating of the two winding transformer divided by kV rating of the auto transformer. So it will be 1 minus K. It will be also reduced per unit full load loss as auto transformer divided by per unit full load loss as a two winding transformer. Now the impedance drop, again the same thing. When the two winding transformer is used in auto transformer, both LV and HV winding are utilized completely. In addition, the current and the voltage rating of each winding section remain unaltered. It will not be changed like this. Therefore, the impedance drop at the full load is same in both the transformers. Impedance drop will be the same. Their per unit values are, however, different. When referred to high voltage side, the per unit impedance drop as an auto transformer is with respect to the voltage V1. Because you can see from here, per unit voltage drop will be referred to this V1, but here per unit voltage drop, which is same, is referred to only this VAC, that is V1 minus V2. So in case of, and for the two winding transformer, it is with respect to V1 minus V2, that is V1 into 1 minus K. So per unit impedance drop of an auto transformer will be equal to I1 Z1 divided by V1, and per unit impedance drop as an two winding transformer is I1 Z1 divided by V1 minus V2. This I1 Z1 will be cancelled out because they are both same in the both windings. So it will be equal to V2 minus V1 divided by V1 is equal to 1 minus K. This is also reduced in the auto transformer. So when the impedance drop referred to low voltage side, the winding current is I2 minus I1, and the auto transformer it is I2 as the two winding transformer. Again, we can use this type of the equation. So per unit impedance drop of an auto transformer in the secondary winding is I2 minus I1 into Z2, and per unit impedance drop in the two winding transformer is I2 Z2 divided by V2. You can see from here. Here we have the winding here. The current flowing through this winding is I2 minus I1, and the voltage is V2. So the voltage drop here will be I2 minus I1 into this Z2. So per unit voltage drop will be I2 minus I1 divided by this V2. So this will be in case of we can say this auto transformer. In case of two winding transformer, In case of 2-winding transformer, you will see that this will be slightly different. Per unit impedance drop of a 2-winding will be equal to I2 minus this Z2 divided by V2. So it will be equal to I2 minus I1 divided by I2. This is also equal to 1 minus K. So voltage regulation. Voltage regulation is transformer is proportional to per unit impedance. So regulation is proportional to impedance drop. It will be also equal to 1 minus K. The only thing that we need to look about is the short circuit current. So per unit short circuit current is reciprocal of the per unit impedance, or we can say it is directly proportional rating of the transformer. So per unit short circuit current of an auto transformer divided by per unit short circuit current of a 2-winding transformer will be equal to 1 divided by 1 minus K. It is directly proportional to the rating of the transformer and inversely proportional to per unit impedance. So the value of the K used above relation is less than 1. In general, for using these relations, the value of K for step down or step up transformer is usually kept as always. K will be equal to low voltage winding divided by the high voltage winding number of turns, or low voltage divided by high voltage, so that K will be less than 1. I think it is enough for today. I'll stop over here. Thank you.